If you pass a beam of white light through a glass prism, the glass bends the light and smears it out into an unbroken rainbow. This is a continuous spectrum, where every possible wavelength of visible light flows seamlessly into the next. Matter does not always emit light in a continuous smear, however. If you pump energy into a sample of gas, like heating it or passing an electric current through it, the atoms absorb that energy. As they return to their normal state, they release that absorbed energy back out as radiation, creating an emission spectrum. Normally, we observe visible light as a complete, unbroken spread of wavelengths, stretching from red all the way to violet. This chart compares that standard continuous spectrum to the emission spectrum of gaseous hydrogen. The continuous rainbow is gone. In place, the hydrogen spectrum shows almost entirely black space, interrupted by only a few sharply defined lines of colored light. The massive dark gaps represent forbidden zones. The hydrogen atom simply refuses to emit light at any of those missing wavelengths. These specific, discrete lines form a unique atomic fingerprint. In the late 19th century, physicists could clearly read this barcode, but they were faced with an observational anomaly. They had absolutely no idea what mechanical structure inside the atom was generating it. To study these phenomena, 19th century chemists relied on instruments like the brass spectroscope. By passing the light from a heated chemical sample through the instrument's internal prisms, scientists could isolate the exact wavelengths being emitted. These specific frequencies act as unalterable identifiers for the chemical elements. The German chemist Robert Bunsen pioneered this technique. Bunsen utilized precise line spectra to identify and discover entirely new elements, like rubidium and cesium, purely by mapping their unique light signatures. Yet this science remains strictly observational. Spectroscopists could confidently categorize these light signatures, but they lacked a physical model to explain why an atom produced such rigid, isolated lines instead of a continuous glow. Without a structural theory of the atom, deciphering the light spectrum became an exercise in pure mathematical pattern matching. Hydrogen became the primary target for this effort. Because it possesses the simplest line spectrum of all the known elements, physicists reasoned that cracking its mathematical code would be the crucial first step to understanding atomic mechanics. For decades, science possessed the capability to read the chemical barcodes of the universe. They could accurately record the output of the machine, but the machine itself remained a black box. This chart shows the complete collection of hydrogen spectral lines, extending well beyond human sight into both the ultraviolet and infrared regions. By analyzing the spacing of these emissions, scientists grouped the lines into specific, named series: the Lyman series in the ultraviolet, the Balmer series in the visible region, and the Paschen series in the infrared. Because it falls squarely in the visible spectrum, the Balmer series was the first to be mapped out and mathematically decoded. In 1888, Swedish spectroscopist Johannes Rydberg formulated this equation, successfully predicting the exact position of every line across all of these series. Instead of calculating wavelength, the equation solves for wave number, represented by the symbol nu-bar. Wave number is the reciprocal of wavelength, meaning the number of wave cycles per unit length. The formula is anchored by a highly specific empirical value, 109,677 inverse centimeters, now known as the Rydberg constant for hydrogen. To execute the calculation, the variables n1 and n2 must be strict integers, whole numbers like 1, 2, or 3, and n2 must always be greater than n1. If you want to find the exact wave number for the prominent red line in the Balmer series, you simply plug in n1 equals 2 and n2 equals 3. The formula perfectly pinpoints the location of that specific color. As a predictive calculator, Rydberg's equation was flawless. However, it was built entirely on observational trial and error. The formula predicted the data, but no one understood why the strict integers were necessary, because those numbers possessed no known physical reality. In 1913, Danish physicist Niels Bohr sought to resolve this glaring disconnect. His objective was to construct a physical model of the hydrogen atom that logically required Rydberg's mathematics to exist. Bohr based his model on Max Planck's concept of quantized energy, the theory that energy is transferred in discrete, indivisible packets. Applying this logic to the atom, Bohr proposed his first major postulate. An electron can only orbit the nucleus in specific stationary states with fixed energies. He defined these states using integers, 1, 2, 3. These are the principal quantum numbers. Bohr calculated the precise energy of an electron in any given orbit with this formula. The energy at state n equals negative RH times 1 over n squared. Here, RH is a constant holding the value of exactly 2.18 times 10 to the negative 18th joules. Radiation is emitted strictly when an electron drops from a higher initial orbit to a lower final orbit. As it falls, the atom sheds the excess energy by ejecting a photon of light. The precise energy of that ejected photon is calculated using an energy gap formula. Delta E equals final energy minus initial energy. Because the orbital tracks are rigidly fixed, the energy gaps between them are identical every single time. The hydrogen atom is structurally locked into releasing exact photon frequencies. This physical mechanism is what generates the isolated lines of the emission spectrum. Bohr had successfully designed a physical theory. Now he had to execute a step-by-step algebraic proof showing that his theoretical energy model derived Rydberg's empirical observational constant. We start by comparing them side by side. On the left is Bohr's combined equation for the energy gap between an initial and final orbit, yielding a result in joules. On the right is Rydberg's empirical formula. To equate them, we must convert Bohr's energy measurement in joules into Rydberg's observational unit, which is wave number. Based on Planck's relation of energy to frequency, we divide Bohr's energy equation by Planck's constant, h. This gives us the frequency of the emitted photon. Next, we divide that frequency by the speed of light, c. This successfully isolates wave number on the left side of the equation. Now look at the constants sitting outside the brackets on Bohr's side. Bohr's energy constant divided by Planck's constant and the speed of light. Let's run the calculation on those three physical constants. It calculates to exactly 109,677 inverse centimeters. The two formulas are identical. This algebraic unification proved that the arbitrary integers n1 and n2 in Rydberg's formula were not mere mathematical tricks. They represented literal physical energy orbits inside the atom. Bohr's model successfully rationalized the entire hydrogen spectrum. Drops terminating at the n equals 1 orbit physically produced the Lyman series. Drops to n equals 2 generated the Balmer series, and n equals 3 produced the Paschen series. However, while flawlessly describing a one-electron system, the mathematics fractured when applied to anything heavier. When observing helium, possessing 2 electrons, sophisticated techniques revealed single spectral lines actually split into doublets, 2 closely spaced lines that Bohr's rigid orbits could not account for. Furthermore, the model failed completely to explain the Lyman effect, a phenomenon where spectral lines physically split apart when the atom is exposed to a magnetic field. Bohr accurately proved that energy was quantized, but his visual framework, electrons operating as tiny planets on flat circular tracks, was far too restrictive to accommodate the actual complexity of atomic behavior. To address these fractures, physics required a completely new mathematical vocabulary. In 1926, Erwin Schrödinger developed a wave equation that discarded the concept of rigid tracks, using wave-particle duality to calculate an electron's distribution in space. Simultaneously, Werner Heisenberg's uncertainty principle proved it is impossible to know both the exact position and momentum of an electron, invalidating the definable orbit concept. The two-dimensional planetary track was replaced by the atomic orbital, a three-dimensional probability cloud that defines where an electron is mathematically allowed to exist. The literal orbits were abandoned, but Bohr's foundational discovery survived. The hydrogen spectrum provided the physical proof that on the subatomic scale, energy does not transfer smoothly. The atomic universe operates entirely in discrete, quantized steps.